In the previous lecture, we introduced complex numbers and its algebraic operations, addition and multiplication. Let me start recalling the previous definitions which we have introduced. First, let me again repeat the definition for complex numbers, which we denoting by C. It contains set of all elements a plus I b, where a and b comes from real numbers. And what we said is if the two complex numbers are equal, that is a plus I b equal to c plus I d, this is equal if and only if, this is again a definition. So, if a equal to c and b equal to d. Under this say equality relation, what we showed is we can identify each complex number to a ordered pair, that is a comma b, from the plane R2. Let me recall the operations, that is addition. So, the addition of two complex numbers defined as you sum the real part and the imaginary part, and the multiplication which we defined as plus I times A d plus B c. Okay. So, with respect to these two operations, we mentioned that it satisfies closure law, associative law, commutative law, and identities as well as the inverse they are exist, and distributive law satisfies. So, with respect to this plus and the multiplication, the complex number system becomes a field, it is a field. And what are the other remarks we noticed? Considering this as the product in the complex number system, we observed I square. If you remember, though we started I is an imaginary number, we identified with the in the plane that is nothing but 0 comma 1. So, which means it is no more a imaginary number. We are able to identify the complex number system with the plane. Any number in the complex number system, we are able to associate an element in the plane. So, with respect to this particular dot product on this complex field, what we observed is I square becomes minus 1, and similarly one can verify that if you consider just the points on the real line, that can be written as a plus I 0, that is simply we will denote it as a dot with b plus I 0. So, under this multiplication we can just see that it is a b, this is a product in the real numbers, plus I 0, which we are going to denote just by a b. And if we consider say the imaginary numbers, that is say I b dot product with I d, then we can show that with respect to that product it becomes minus b d, okay, plus I 0, this we are going to denote just the real part. Okay. And with this say multiplication, what we can really actually see is that the a plus I b and c plus I d I can do direct multiplication now. How do I define the product? So, now I can, how can I do it? So, here A is a complex number, it is carrying only the real part, and IB is a purely an imaginary number, and similarly C is another complex number, but just only with the imaginary part is 0. So, we can really see that this is Z1, this is Z2, this is Z3, Z4. Now, this particular product you are going to use the distributive law, that is A dot. So, the Z1 multiplied with this C plus ID plus IB multiplied with C plus ID. Now, we see that this is again further say distributive law, further one more time you apply, this is AC plus I AD plus here IBC minus BD, all together we just receive what we defined as a product now. So, what is the message? Message is, so let me just see that here we define the product in this manner, then the resultant vector is a complex number, then we verified all the laws, and then using the say properties of this field axioms, now we are able to see that. So, no more say need to remember the product, just do the as usual the product, and here we used the fact that is I square is minus 1. So, using this fact we can basically do the as usual product. Okay. Now, let me just introduce some more notations. One is say the real part of, so let us just say that Z is A plus IB, real part of Z which is defined as RE re Z which is A. So, real part of Z is A and imaginary part of Z which is use the notation IM Z which is B, and if say let us say this is 1, 2, third, if suppose the real part of Z is 0, then we say that Z is purely an imaginary number. So, either we say it is purely an imaginary number or just an imaginary number. Similarly, if imaginary part of Z is 0, then we say that Z is purely real. So, with this simple notations, let me start with the new definition, that is conjugate of a complex numbers. So, conjugate of complex number is defined by Z bar, conjugate of Z where Z is A plus IB, where the notation used as Z bar which is given by A minus IB. Okay. So, this is definition for Z bar. Let us see what it means. So, we have the complex plane and let us consider the point z, that is a plus I b. So, which means in the imaginary unit it is I b and on the real unit it is a. Now, z bar denotes exactly, we are taking the unit which is minus I b and z bar we are denoting as a minus I b. If we see this is nothing but mirror image of z with respect to the real axis. So, z bar is nothing but is mirror image of z with respect to we can say x axis or the real line. Let us see simple example. Suppose z is, let us say that 2 plus 3 I, z bar is just 2 minus 3 I, and suppose you have say just it is a real number, purely a real number, let us say 5, z bar is there is no change, which is just 5 because it is lying on the real line. So, its mirror image is again on the line itself. So, let us see some properties. Suppose say z equal to z bar if and only if z is a real number, or in other words, so the meaning of this one, just the imaginary part of z is 0. Okay. So, if we see that, so the z equal to z bar, which means after applying the mirror image we get the same number, then it must lie on the real line, that is what we are claiming. So, if z is a plus I b, then suppose z equal to z bar, what does it mean? It means that a plus I b is a minus I b, then it is immediately clear that we are demanding two complex numbers to be equal, then the component wise must be same. So, the first components anyway it is equal. So, or just the by field axiom you can cancel a, then what you get is it is 2 times of I b equal to 0, and this happens if and only if b is 0, that is nothing but imaginary part of z is 0. Okay. So, what we observed is a simple proposition, whenever z equal to z bar, then it must be a real number. So, this particular say argument we will use frequently to say a complex number is a real number. It is just enough to show that z equal to z bar. Okay. Such idea will be frequently used to show a complex number is a real number. Property 2, if we apply conjugation for z bar again, so we return back to z. Okay. This is again it is a straightforward, let z is a plus I b, then the z bar is a minus this, and this can be seen as just say minus b, and z double bar. So, again you take its conjugation. So, what we see is that again say this is plus I and then minus of minus b. So, we see that it is again, of course, what we are doing is this is a obvious one, we are trying to write an argument. Okay. Third proposition, if we consider sum of two complex numbers, take its conjugation, this is same as Z1 bar plus Z2 bar. This is again say easy to visualize, say let us say that Z1 is A plus IB and Z2 is C plus ID, then Z1 plus Z2 bar, which is A plus C plus I times B plus D whole conjugation. By definition, this is A plus C minus I B plus D, and which basically gives us, which we can write it as A minus B plus C minus I D. This is nothing but Z1 bar plus Z2 bar. Fourth property, that is, it is always that for every Z in complex number, Z into Z bar is always a real number, is a non-negative. Real number. So, it is clear that, so let us consider Z as say general element, which is A plus IB, and we consider its conjugation. By multiplication we can just verify that it is A square plus B square, and each term is non-negative. So, the sum is again non-negative. So, from this particular proposition, what we can observe is, suppose like a comment or a remark, suppose you have Z1, Z2, their product is non-zero, okay. Then we can in fact conclude that both Z1 and Z2 both are non-zero. Okay. So, the proof, I leave it as an exercise, think about this. So, what you observe is the previous property, when you multiply by its conjugation, it gives a non-negative real number. You use this fact to conclude this particular remark. Fifth property, that is Z1 into Z2 bar, it is Z1 bar into Z2 bar. It is easy to realize. So, let me just consider Z1 Z2 bar. First you take the product and then take its conjugation, which is same as take the conjugation for each complex number, then do the product, both will be the gives the same complex number. So, let us consider first product of two complex numbers A plus IB multiplied with C plus ID, and then take its conjugation. We know what is this product, this is AC minus BD. So, after conjugation you are going to get minus I AD plus BC. You can verify that this product is nothing but coming from A minus IB and C minus ID, which is nothing but the Z1 bar into Z2 bar. The next proposition, Z inverse conjugation, which is same as first take the conjugation and then take its inverse. So, what we are asking is, if you take the conjugation for Z inverse, what do you get? It is basically same as, first you take the conjugation for the complex number and then take its inverse. So, it is like this operation is commutative, right. Let us just try to realize this. So, what we have by definition Z inverse, it means that, of course, here we need Z must be non-zero. So, by definition Z inverse, it means that multiplying with Z we get 1, and now you apply conjugation by the above property. So, we apply conjugation for this product element, right hand side is a real number. So, it gives the same element, and the product conjugation is same as, you take the conjugation first and then take its product, it again gives 1. It means that Z inverse bar is inverse for the Z bar. Okay. So, that is exactly what we like to prove. This concludes that Z bar inverse is same as Z inverse bar, right. The seventh property, which is, you consider Z1 by Z2, take its conjugation, this will be same as Z1 bar divided by Z2 bar. Again, to make division make sense, we need to assume that where Z2 is non-zero. So, this relation again it follows from the above one. So, combining the 5 and 6, say from 5 and 6 we can derive the following, that is Z1 by Z2, the whole conjugation is given by, this can be realized as Z1 product with Z2 inverse. So, I am writing the Z2 inverse is nothing but, I am just, this is again a notation, 1 by Z2 it means it is Z2 inverse. So, its bar, proposition 5 says that this can be taken bar to each factor, that is okay. This is product with Z2 inverse bar, and this basically we get it as, because the above proposition we see that it is Z1 bar multiplied with Z2 bar the inverse. Let me again just repeat that. So, this is bar, finally what we concluded is Z1 bar into Z2 bar the inverse. As I mentioned, this is nothing but the inverse factor, we write it as 1 by Z2 bar. Okay. So, proposition 8, maybe it is just a comment here or a remark. Okay. When we write 1 by Z, okay, the notation 1 by Z, it means that it is just the Z inverse. Okay. Again, what is Z inverse? Z inverse is an element which is, when you take product with Z, it gives 1. Okay. So, in this particular sense we write it as Z inverse as 1 by Z, okay, just to cancel, so that you get 1. So, it is just a notation that 1 by Z, it means that it is Z inverse. And one more further remark here, that, so once we commented about Z inverse, let us just see that 1 by Z we can multiply and divide by Z bar, then what you get is, it is Z bar divided by Z into Z bar. So, we know what is this factor, this is A minus I B, and a square plus b square, where z is written by a plus I b. So, what we, if you recall, when we calculated z inverse, we tried to solve the equation to find out the value for the z inverse. Now, we see that by using the factor z bar, we are able to compute the z inverse easily, just by multiplication and dividing by z bar, we are able to calculate z inverse, that is the a by a square plus b square minus I b a square by b square. Proposition 8, this is simple one, that is real part of z can be written as z plus z bar by 2. Similarly, the imaginary part of z can be written as z minus z bar by 2 I. Okay. It is just merely the definition that if we consider z, this is nothing but real part of z plus I times imaginary part of z, and its conjugation is real part of z minus I times imaginary part of z. Now, it is clear that real part of z is nothing but z plus z bar by 2, and similarly imaginary part of z is z minus z bar by 2 I. Let us do a simple problem. Complex number x plus I y satisfies this equation, that is square root of a plus I b plus c plus I d, then show that these numbers x y, that is x square y square the whole square, gives you a square plus b square by c square by d square. So, what we see is that suppose the complex number x plus I y, that is equal to square root of a plus I b divided by c plus I d, then we are able to derive this relation. So, we need to prove this. I say that z is a square root of some b. By definition, z square is b. Okay. So, we know what is the meaning of z into z, and that should be equal to the b. Okay. So, whenever there is a z satisfies this equation, then we write it as z equal to square root of b. So, by given assumption, what we get is, it is x plus I y the whole square must be equal to a plus I b divided by c plus I d. So, now the complex number, so if you see the identity, there is no complex value is involved, just finally it is a real number equal to this factor. Okay. So, now as you remember, the one of the property is when we multiply z with z bar, that gives a non-negative real number. Okay. That gives a hint that maybe we can multiply with the factor which is exactly its conjugation. So, the conjugation for the same complex number, here let us say this is z, we are multiplying by z bar, then again by the previous properties, when you take z1 z2 bar is given by z1 bar multiplied by z2 bar. So, by this relation you will see that immediately it is x plus I y the square multiplied by x minus I y whole square. And now this can be done by the associative law. So, you just write down what is the meaning of this. This is x plus I y multiplied by x plus I y, further here x minus I y multiplied by x minus I y. We know the product, it is x minus x plus I y multiplied by its conjugation gives x square plus y square. So, we get x square y square the whole square, right. So, this is basically the left hand side. So, the LHS what we considered, and similarly correspondingly the right hand side, what do you have? X plus I y the whole square is a plus I b c plus I d, and we are taking its corresponding conjugation. Conjugation we know z 1 by z 2 bar is given by z 1 bar divided by z 2 bar, which means it is a minus I b c minus I d, and the product it gives a square plus b square, and this is c square plus d square. So, by given assumption these two are equal. So, we get the required relation. So, that is x square plus y square the whole square is a square plus b square by c square plus d square. So, using the property of multiplication one can derive the following simple identities, namely z 1 plus z 2 the whole square. Let me just write down directly what we have this product. This is z 1 plus z 2 product with z 1 plus z 2. By distributive law z 1 is multiplied with z 1 plus z 2 plus again z 2 multiplied with z 1 plus z 2. Again you use the distributive law. So, we are using twice distributive law, that is z 1 square plus z 1 z 2 plus z 2 multiplied by z 1 plus z 2 square, and the product is commutative. So, these two factors are equal, z 1 square 2 times of this. So, what we derived is like in the real line real numbers, when we take a plus b the whole square we get a square plus 2 a b plus b square. Same formula holds for the complex number as well. And so, which means once you see this result, then you can say prove the other identities like z 1 plus z 2 the whole cube gives z 1 cube plus 3 times z 1 square product with z 2 3 times z 1 z 2 square plus z 2 cube, and z 1 square minus z 2 square can be written as z 1 minus z 2 z 1 plus z 2. So, what we are essentially trying to say is when you are doing this operation, it is not necessary that you combine first a real part you sum and then again the imaginary part you sum up and then you take the product. This is not necessary. So, this is basically like whatever identity it gives, it is similar to the real number system, we are able to work our say algebraic operations. One simple exercise, let z 1 z 2 be two complex numbers, then show that z 1 multiplied by z 2 bar and then combine z 1 bar to this is a real number. Now, let us do another problem. Here we are given with say 3 complex numbers. If the sum of sum and product of three complex numbers are real, then which of the following is possible? Following is are possible for some, say possible for some pair of 3 tuple Z1 Z2 in complex numbers. So, what is given here? We are considering 3 complex numbers, their sum and product gives a real number. So, now our question is, which of the following is possible? First choice is exactly one of the 3 numbers is non-real. Exactly two of the 3 numbers are non-real. Third choice, all 3 numbers are non-real. Fourth choice, all 3 numbers purely imaginary and non-zero. So, let us look back our question. We are given with 3 complex numbers Z1, Z2, Z3, their sum is real and their product is real number. Now, let us look at the first choice, whether this is possible. Exactly one of the 3 numbers is non-real. Is it possible? Answer is no. So, A is not possible. So, here the statement says you consider at least one as imaginary number, remaining or can be real number. So, which means that whenever we have a set with Z1 which is not a real number, that is Z1 not equal to Z bar, which means it is a complex number. So, that is the imaginary part is not 0, okay. And the remaining say Z2 can basically choose it as real numbers. Let me call it as A and B, where A and B from real numbers. Then immediately I see that Z1 plus Z2 plus Z3, what you are having is just the Z1 plus A plus B. Certainly it is not a real number. The reason is Z1 contains a imaginary part which is not cancelled by other term. So, that remains as it is. So, which means it is not a real number. So, the possibility of A is ruled out. Let us see the possibility of B. Exactly 2 of the 3 numbers are non-real. Okay. So, whether we could provide 2 set of pairs which is say they are complex numbers together a real number will satisfy our given condition. Okay. So, let us see that. So, what we are demanding is you give me 3 pair. So, the sum must be real. I am just repeating the what is our given assumption. Okay. So, we are looking for a triple which satisfies this condition. So, here what we can do is we can make a choice. Once you have a Z1, we can take Z2 as its conjugation, then their sum become a real number. So, Z3 we can leave as it is a real number, then you have basically like it looks, this is possible. So, which means I take Z1 as fixed example, I take Z2 is its conjugation and Z3 is, let us say just simply 1. Then what I know is their sum is real and together Z3 gives a real number. Further, when you are taking the product Z into Z bar, we know it is a non-negative real number, then product with Z3 again a real number. So, this is basically like it satisfies, yes, this is possible. So, choice C, all 3 numbers are non-real, it is again possible, yes. So, just basically like I give you one set of pair, maybe you can try with the other set of pair where it satisfies this relation. So, the one set is just consider 1 minus I, Z2 as again the same number and Z3. Now, you see I am just going to manipulate. So, when I sum it up, what I get is say here minus 2I. So, what I need to do is when I sum it up, it must be a real number. So, naturally I make a choice 2I, but further of course, we need to see that whether the product is a real number. When you do the product, so Z1 into Z2, we see that it is say exactly Z square. So, Z square it is say 1 square plus I square, that is minus 1 and minus 2 times of I. So, what you get is minus 2I. Now, when you product say what you are getting is a real number. So, what is the exercise for you is you find the other set of pair where it satisfies this. Okay. D is again I leave it as a exercise, but I will write down the answer. Answer is again this choice is not possible, but you try to do it. So, let me just summarize. What we have done is we introduced conjugation of a complex number and we studied several properties. Now, what we will discuss is modulus of a complex number. So, first let me recall how do we define the modulus for real number system. So, for A in real numbers, we define modulus of A as A if A is non-negative, minus A if A is less than 0. Okay. The same one we could also write it as maximum of A together with minus A. Okay. So, this gives the modulus definition. Now, question is similarly can we do for the complex number system. Okay. So, once we see the first definition or even the second definition, they related with the relation, that is basically you are comparing a number with 0, then we basically define this modulus. Question is can we really have a say the less than relation in the complex number system. Okay. Answer is no. So, let me just have a quick say idea that we cannot have a sort of a relation, that is the ordering what we have in the real number, which cannot be possible in the complex number system. So, I am not writing in detail, but let me just give us some rough idea. Okay. So, idea for, so first let me write there is no less than, which means we cannot compare two complex numbers in C. Okay. So, just a idea is if suppose there is a relation less than, okay, then if suppose there is a relation in C, then what will happen? Any number can be compared with the other number. For example, in this case, so either, so what we end up immediately, either I is less than 0 or I is greater than 0. Okay. So, once we have this, of course, we no need to basically like consider this particular relation. Directly we could start with say either this, or actually we could directly say that I square must be greater than 0. The reason is, whenever you have a order relation, we can show that a number multiplied by itself will be non-negative if there is a order relation. Okay. So, which means I square must be greater than 0, but I square we know it is minus 1, which is less than 0. Okay. So, which means this particular relation will tell you that minus 1 is greater than 0, but we have this, that is contradiction. Okay. So, what we are encountering? We are encountering that we are not able to define the modulus as usual like in the real line, but we can basically try to see what it physically represents. Okay. Then we maybe can associate modulus in a different sense. So, when we are taking a real line, there is a, it may be a positive number, may be a negative number. The mod A always say mentions the distance from 0. Okay. So, similarly like if it is say whatever you have, if you have a negative number, let us say minus b, then still basically like what it says is mod b says the distance between 0 and minus b. Okay. So, with this distance as an idea, we can try to think for a modulus for a complex number. So, let z be a plus I b, then consider a point z equal to a plus I b. So, here say the length here it is b, which is basically the unit here which is I b, and here the length is a, and what we have 0. Now, we are trying to associate mod z. Okay. So, we would like to define modulus of z, okay, that is denoted by this notation. By Pythagoras theorem, we know that what is the distance for this. This is distance is given by square root of a square plus b square. So, it makes sense now we are trying to define modulus as a distance from the origin to the point. Okay. So, the modulus which is defined as square root of a square plus b square. Now, what we observe is immediately that it is always a non-negative number, and one more point. So, if we see the association to the R2 plane, then this point we know that it is a comma b, and this point we know that it is 0 comma 0. Then the distance between these 2 points, which is given by Euclidean distance, which is also coincide with the what we have written. Okay. So, what we are doing is it is consistent with the what we have the association with the R2 plane. So, let us see simple example, that suppose z is a 1 plus I, then mod z by definition it is 1 square plus 1 square. So, you get root 2, and if suppose Z is just a real number, let us say 5, then mod Z is just the phi square. Again what we associate is the positive number, because we are seeing it as a distance. So, which is phi, and if Z is some purely, okay, let us just consider Z equal to I, mod Z is square root of 1 square, right. So, with this simple examples, let us see some properties for modulus function. Let me just summarize what we have done. We introduced conjugation of a complex number and we studied its properties. Now, we introduce the modulus of a complex number, which associates a distance from the origin to the complex number. The further properties we will discuss in the next lecture. Thank you.